Hello everyone, welcome. So here I am going to explain the Vedic multiplier on Fpga kit. Basically we are going to explain 2-bit binary Vedic multiplication on Fpga Sparten kit. So before going to the implementation on Fpga kit, we have to understand what is Vedic multiplication. So Vedic multiplication is basically a fast calculation technique which provide basically mental calculation with some basic rule and principle. So let's see with the help of some example how this Vedic multiplication can be done. So suppose we have to multiply 2-bit binary number, let's say this A1 and A0 and B1 B0. These are the 2-bit binary number, right? So we have to multiply this 2-bit binary number. So suppose if we take maximum, the maximum value of 2-bit binary number will be 1 and 1, and the B is 1 1. In decimal, the equivalent value is 3, and the equivalent value of maximum value of B is 3. So on multiplying these two we get 9. It means we have required maximum 4-bit number to multiply this 2-bit binary number. Let's say this 4-bit are M2, M1, M0, and this one is M3. This 4-bit will be the result. Now see how this multiplication is done. Suppose the first step will be step first, A1, A0, B1, B0. First step will be the multiplication of LSB bit of both number, right? Suppose the value of A0 is 1, let's say the value of A01 is 1 and B0 is 1, then by multiplying 1 and 1 we get 1. If the value of A0 is 0 and B0 is 1, then the value will be 0. If the value of A0 is 1 and the value of B0 is 0, then result will be 0. But we observe that the result of the multiplication of LSB bit is either 1 or 0. It means to multiply this 2-bit number we required one AND gate, 2 input AND gate whose input is the LSB bit of both number A and B, that is A0 and A1, right? And we get the output as M0, yani multiplication LSB of multiplication bit, right? Now there is no carry, so for the multiplication of LSB bit only one AND gate is required. Now step 2 will be step 2, A1, A0, B1, B0, right? We can cross multiply this, right, and add this cross multiplication result. Yani step second will be A1 B0 plus B1 A0, right? So to multiply these two, an AND gate is required, right? One AND gate and another AND gate, and for this addition we required an half adder, because and by adding this, suppose the value of 1 1 is 1 1 and this one is 1 1. So if you add this number we get carry. So to generate carry we required one half adder, right? So to implement the second result we require half adder, right? The input of half adder is the input of AND gate, in which the first 2 input AND gate is A1 B0 and the second input of AND gate is A0 B1, and we get sum and carry. So sum will be the result of second bit of the result M1. Sum will be M1, and keep the carry for further next step. So in second step we required 2 AND gate and one half adder, right? Half adder is required because suppose if the value of this 2 is 1 1, then there is a carry, so to keep carry we require half adder. Now step 3 is step 3 A1 A0 B1 B0. Step 3 is the multiplication of MSB bit, right? So to multiply these 2 bit A1 A2, we require AND gate. Any one AND gate is required, 2 input AND gate, right? But there is a carry C1 which is from step 2. We have to add this carry with the multiplication result. So to add this carry and to add this, we require another half adder, and the result will be sum and carry. So this sum is the multiplication of third number of multiplication, and this carry is the last bit of multiplication result, M3 and M2. So overall we see that to multiplying 2-bit binary number A1 A0 B1 B0, we required 1 AND gate, 2 AND gate, 3 AND gate and 4 AND gate. We require 4 AND gate and 2 half adder, right? So in this way we can implement the 2-bit binary multiplication on FPGA kit by using Verilog module. Now let's see with the help of an example how this can be calculated using Vedic multiplication. Suppose we have to multiply a 2-bit number. Let's say take another example of decimal number, let's say 2 and 5, and this one is 1 and 3. We have to multiply these two numbers. So first, initially what we do is that we multiply 5 with 3. 5 is 3, it means 5 into 3 is 15, carry 1. Now cross multiply this and add, and 3 2 is 6 and 5 1 is 5. Now add this with carry, 5 1 6 6 6 12 2. Again carry, keep it carry for further multiplication. Write this 2 here. Now multiply this 2 1 is 2 and carry 1 is 3, and this way we get the multiplication. Now let's see how the programming is done on Verilog code. For Verilog code, let's see. So to program this, we have to open ISE project navigator. Basically this is the editor for Verilog module. Create new project, write the name of the module, program Vedic 2_bit, whatever will be the name, you can just write the name. Click on next. Now select the family of the device on which we are going to implement, or we are going to dump this file on FPGA board. The family of the module is Sparten3, because we have a Sparten3 module. Device package is XC3S500 is device package is FG320 speed, and click on next and finish. After the finishing this, click on this, select a new source, click on Verilog and write the module of the name which you want to save, Vedic 2. Click on next and finish. After that a Verilog editor will be open. So what done, I already write the program on our PPT, so I just copy paste the program which I have already written. So I have already written the program, so I just copy this and paste into the Verilog code editor. Now click on save. Now here what we see that we have initially defined a half adder, because we see that to implement the 2-bit binary multiplication we required 2 half header and 4 AND gates. So initially we have to initialize the function of half header, how this is working. So I have initially define a code for half header and initiate this half header into our main program, right? So now further check the syntax error, whether the written code is correct or not. Click on synthesize, double click on synthesize, a running process will start running. So it will take some time, so I will skip the videos for fast forward. So when synthesis process is done, there is a green tick mark on synthesize. Click on plus, now click on view RTL schematic, in which we can see the by which AND gate we can implement this program. So click on RTL schematic, click on wizard, okay, then add Vedic to create schematic. We can see the schematic of the program code which I write on the program editor. Double click on that and click on this. We can see that there is a AND gate and half header. So in this way we can implement this program. Now click on view technology schematic, in which we can see the technology of the program. Click on that, add create schematic, double click on that. So here we can see the LUT file on which we can write the program on Fpga Sparten3 kit. Double click on that. You can see the internal structure of LUT, in which gate is by which gate we can implement this LUT code. So here we can see the equation, truth table, k maps. So these are the LUT design of our program. So now we can implement this design on, we can dump this program on Fpga board. So before Fpga board we have to connect all the port of Fpga board to our system, so that it can recognize the board. So let's see how this can be done. So before going to implement this, we have to connect all the port, like power cables and the code dumping port, through which we can dump the program into this Fpga code, right? So we can connect this code and switch on this, right? Now go to the user constraint. User constraint, basically we have to, in user constraint we can define the input and output pin of the Fpga. So here we can see that these are this switch are act as a input pin for Fpga, and there are 4 switch here. This also used as Fpga input pin for Fpga gate, right? And the LED here, what observe that act as output for the Fpga port. So click on anyone input output planning. So click on yes. So it will take some time. So when the plan head file is open, now the plan head program will initialize the project. Basically it will map the Fpga kit into the program in our software, so that we can give the input pin and output pin to the Fpga code. So it will take some time. So when the process is done, this type of interface is open. Now click on schematic. We can see the LUT file on this here. So we have to give the input, and we have to define the input and output pin through which we can give input and take output. So click on IO port. So here we have to write the site name of input and output. Basically we have to give the pin name where we give input and the port name where we take output. So basically this is the input pin, like L11, L13, L14. so click fill this pin into that site name. First one is A0 is N17, so we can put this N17. Next one is B0 is L14. Next one is B1 we take L13. And next one is A1 we take H18. Right, H18. We have to put H18. Now for output is taken from this LED, like F12, E12, E11, F11. So for M0 output we take F12. Now for M1 we take E12. Now for M3 we take D11. Now for M2 we take E11. Right. Now we have to change the value of this default value to LV CMOS 33, so that VCO can change to 3.33. okay, so select all this default value to LV CMOS 33. So I have changed all these to LVCM CMOS 33, so that our VCC will change to 3.33. Now save this constraint file. Now open our project editor. Now here click on this. Here we see that there is a UCF file on which we can write the code for input and output. Double click on that. Click on yes. So we see that there is a pin defined for which we can give input and take output. Now what we do is that click on this. Now click on implement design. It will take some time, so we can fast forward this. Once the implementation process is done, click on plus. We see that there is a green mark on touch step and place root. It means our implementation process is successfully. Now click on generate programming. Here we see that there is a generate bitstream. Basically this is the bitstream file which is dumped into our Fpga Sparten3 kit. So it will take some time to create our bitstream file, so we can fast forward this video. So once the process is completed, you can see there is a green tick on generate file. It means our bitstream file is generated. Now we have to configure device. So click on configure device, and before configuring device we have already told that all the port of our device should be connected. So it will take some time, so we can fast forward this. So once the impact is open, we can see this is our configured target device on which we can see the IC of the FPGA kit on which we have to dump our program. Click on boundary scan, right click on this and click on installation. So basically installation means it will take all the ICs like Xilinx ISE 1, 2, 3. So we have to click yes and select the bitstream file. So these are the bitstream file which we have generated. Vedic 2-bit open. Now we see that here this is the Xilinx Sparten 2 in which we have to dump file, and this and we does not require any SPI or BPI files, so we have to click no and bypass all this. Now click on FPGA and the package name is XC3S500E. Select FPGA device specific programming property, click apply, now click OK. Now the program is fed into this intact file. Now what we have to do is that we have to write this program into our device. So when we click on program, then there is a skipping command. It means this program is dumped in our Fpga Sparten kit. Let's see how this dumping process is done. So on FPGA kit we have to click on this program button so that we can reset this FPGA kit. Click on this. When we click this, there is a blinking. It means all the program which already have burned is erased. Now go to the program, right? Go to the program and click open. Double click on program. When we double click this, there is a blinking on FPGA board. It means the program is dumped into our FPGA board. It shows there is a blinking. It means the program is successfully done. Now initially we already told that we have take input from this switches. So suppose we have to give this, there is a blinking of LED. It means our output is showing. Now let's verify the code into by taking some inputs. Suppose we give A1, A0, B1, B0 all to 1. We have to show 9. It means 1, 1. So this is successfully compiled. Our program is successfully verified. Now we can also see this verification on this code editor Xilinx software by simply writing the test bench and simulating this. So let's see how this program is simulated on by writing test bench. So for test bench we have to take a new source and Verilog test fixer. Write the name of test bench, Vedic test, click OK, next, finish. So it will take some time to create the test bench file. So the test bench editor is open. Now here we have to give input. Suppose we take input as 2-bit number 1, 1, and B also take 2-bit number as 1, 1. And 1, 1, right? Now click on simulate, select this, and here simulator, click plus and check the behavioral syntax. It check whether the test bank written is correct or not. Double click on that, click on yes. it will take some time, so I fast forward this. So finally here it show green tick mark, it means our syntax written for the test bench is correct. Now simulate the behavior model, double click on that, the process is running. Once the process is completed, the simulator graph is opened. Now we see that by giving input 1 1, output is 1 0 1. Basically the decimal value of 1 1 is 3 and this 1 1 is 3, it means 3 into 3 is 9, then output is 1 0 0 1. Let's see on the same on the FPGA kit. I have taken the output as pin number. We can see the output in your UCF file that M0 is F12. Here F12 is M0 and F12 is M0 and M1 is E12. M1 is E12. E12 is this pin is E12 and M2 is let's see the M2 is let's see, okay, so M2 is this pin and M3 is our D11 pin, right? M2 pin is E11. M2 pin is E11. So when all the input is 1, we see that the F12 is blinking. It means F12 means let's see with the help of this F12 is 1, it means first bit is 1 and second bit is 0, third bit is 0 and fourth bit is 1. It means the output result is 9. So the code which we dumped into our FPGA Sparten 3 kit is verified. Thank you.